Yes? So now we moved from the continuous signal to the discrete form. So our analog signal that we hear otherwise in the world has been sampled and digitized and got into the computer. And once there, this is why we can represent it. Not a continuous signal anymore where we have a flowing curve, but discrete numbers with space between them. Either in a stem plot like this or just the dots there. And you notice we don't have time anymore on the axis, but n that represent the sample points in the vector. Because indeed, the function now is a vector. X of n consists of the sample at the value of sample point 0, the sample at the value at sample 1, and so on until the end of the vector. Neat. So once we have it in the computer, maybe we would like to apply a moving average. It's a very common operation if you need to get rid of some noise, for instance, from a sensor or something else. So a simple moving average can also be expressed as a function. Let's call it y of n. And y of n, for a 2-point moving average, could consist of the input signal, the current input signal, plus a previous version, the previous value, so n minus 1. And because we're doing an average, we're dividing by 2, right? So how would this look at for sample 0? We have 0 here, plus, minus 1, and divided by 2. That means that here we end up with minus 5. So that's our sample point for our value for sample 0. For 1, we have the current value, which is 1, plus 0 divided by 2. So, positive. For sample second sample, we have 1 plus the previous, which is also 1. It is 2 divided by 2, so 1. So this stays in the same. And we can continue like this. Here we go. There, there. So something like that is going to be found. What we have here is the difference equation of this moving average filter, because that's what it is. It's a filter. What type of filter is it? Well, you can see that the sharp edges here are sort of being smoothed out. So actually it's a low-pass filter. It's going to be even more clear if we do this with a higher point. So we can extend this to another one where we take the current value of the signal plus the previous and the previous before that, plus the previous before that. Now we have 1, 2, 3, 4, a 4-point moving average. So I divide each of these with 4, so we actually. And what would the output be? So at the current value, Q 0, you take 0 plus minus 1 plus minus 1 plus 0. Each of these by 4. The output is minus 1/4. So here. The next step, Q. We do the same thing, very methodically. Not too difficult anything else. We have the current value 1 plus 0 plus the previous before that, minus 1 and minus 1. These two cancel out. The whole thing divides by 4. So minus 1/4. Sorry, that should have been. We can continue like this, and what we're going to see is that the higher order, the more sample points that we take into this moving average, the more we're going to flatten out the curve. So it's a low-pass filter, and the longer window we apply, the more drastically it's going to smoothen out everything that happens in it. So it's a low-pass filter. And next thing we're going to look at is how to implement this.